This is because of the butter.
Jenna, can you check with Dr. Praino if he can hear us?
I can hear you and I can see the room. Good afternoon.
Good. With that, then we should start in about 1 minute.
That sounds fine.
So when start, you'll check this. Okay. Okay. Dr. Praino, you have you can share your screen when you're ready. You have 7.
I will do that.
It might be nice for him if there was a camera facing us instead of
Yeah.
screen.
Yeah.
That one in the back, yeah.
Can we change that?
And then he can watch his own presentation.
Right.
But
But if you see that,
you know, see that on his screen and then he's got.
right, rather than the actual people in the room.
Sounds like a billion.
Yeah, I was wondering why.
You were, the good stuff is doing so these and the bad stuff is doing.
Special place now for people to do it. Hey guys.
Thanks for talking to you about whether you're going to the AAG.
I asked for some in December.
Our hope is that we'll be.
And Paternoster, so I said, he said, my neighborhood.
Cause we passed a range of people who said, and we have like 4 or 5 minutes to talk, but we want to address.
This one, we still want the mic to be.
The mic's okay.
But that's this mic now.
Okay, so yeah.
I'm like,
What's
just come
good?
or go.
Yeah.
Just come or go.
You still there?
Fine.
So hold the line.
I'll just- So, kind of having almost no other perspective. So, all the way down. I don't understand.
Yeah, I think it still is.
But I hadn't heard from him. But sometimes I'm kind of the organizer of the session.
Oh,
So I was like, okay, well. yeah.
Fly over your
And he was like, do you want?
I can hear
Go for it.
No, you are.
Right.
Can you hear us now, Dr. Praino?
I can.
Okay,
Okay.
great. All right. So.
I'm just curious, can you see me switching screens? Is my screen switching?
Yes.
Yes, it is.
Yes.
All right, great, because I just realized while the focus of the presentation today will be on one particular project, I know that, you know, perhaps to provide a little bit of background, I have a slide or two that I could switch to if need be. I could certainly do it verbally, but if a slide is helpful, I could also do that. But I know the focus of today will be on what you're seeing, the Jefferson project.
Just share your screen, not your application. That should be fine. Then
Right.
whatever you put up, we'll see.
Yes.
All right, everybody. Thank you for coming this afternoon for our speaker series. We have Dr. Anthony Praino, who is our 3rd speaker of the series, and Professor Jana Hauser is going to introduce Dr. Praino. Jana, if you are here and you can see us, hear us, would you mind?
I can see you and hear you. My camera was looking a little foggy. We had a little incident with some water earlier here today, so I apologize for that. I gotta look like I'm in the haze over here. Yeah, absolutely. So it's my pleasure to introduce to us here Anthony Praino. Anthony is a kind of wears a pretty cool hat, both as an engineer and a meteorologist for the environmental sciences team at IBM. At their Watson, and he leads the system and infrastructure engineering, as well as doing research and development in environmental sensing and modeling applications. So since 2000, his focus has been on developing the business of weather in IBM. And this has led to the acquisition of the Weather Company in 2016. Anthony is one of the founders of Deep Thunder, which is one of IBM's 100 icons of progress. Deep Thunder has driven and enabled applications for public sector and energy and utility clients, as well as being an integral part of IBM's weather, climate, and environmental research and development strategy. Anthony has been a member of the Jefferson Project R&D team since its inception in 2012, where he has worked on developing high-performance computing systems and advanced modeling, sensing, and IoT capabilities for water resource and environmental management. His work is focused on applying a unique blend of client experiences and skills in science and technology combined with technical leadership in cross-disciplinary areas of business, environmental science, and engineering for the development and application of advanced analytics and decision support systems for clients and sectors, including government, energy, environment, transportation, agriculture, supply chain logistics, and water infrastructure. So Anthony comes to us with a really nice, well-rounded skill set and area of expertise. So I'm looking forward to hearing what he has to say. So we'll turn the time over to you, Anthony, and looking forward to it.
Thank you, John. I really appreciate that. And again, correct me. I know we're speaking to staff and faculty. Are students included in that? Because I don't recall.
Yes, there are graduate students in there.
All right,
and
great.
Perhaps a handful of undergrads too, maybe.
Okay, great. Thank you. Because yes, some of the presentation, the focus of this presentation has some linkages to particular disciplines and fields that, you know, when I originally put this together was focused on, you know, on students. But I think this gives a good overview of, you know, of one of the research projects that I've had the privilege to work on for about the last 10 years at IBM Research. But in the way of perhaps providing a little bit more background on me, because I think Professor Hauser put it correctly, I'm a bit of a hybrid and somewhat unique, both on my team and just in general in the meteorological community because of my dual academic training in engineering and in meteorology. And again, in the interest of time, I won't go into a lot of detail into how I got where I am, but it might be interesting to provide a little bit more background on me. So I'm going to try swapping screens here to the other presentation just to show a slide or two. Let me know if you can see this. Are you seeing a slide or still the Jefferson Project?
Jefferson Project.
You are, okay. How about now? Same?
Yeah.
All right, yeah, I'm working off of two screens here, and I guess the Mac got confused. So I'll speak then directly to the background as it's relevant. And I think again, I think Professor Hauser provided a good background. Jan and I met at a regional conference here a year or two ago, and I think we had mutual interest in some areas as well as just you know, I'm very interested in reaching out in academia. Part of my mission as a researcher is in academic collaboration, as well as my role or some of the work that I do in the American Meteorological Society involves work on the Board of Higher Education, the Board of Private Sector Meteorologists, as well as what's known as EIPT, Environmental Information Processing Technology. So that speaks more to my technical background, but the BHE is near and dear to my heart because I spent a lot of time doing mentoring undergraduate, graduate students, postdocs, as well as just in the educational arena. I joke that I guess when I finish my day job here at some point in the future, I'd like to get more involved in educational endeavors. So I try to spend, you know, some of my time doing that. So it's really a pleasure for me to be able to present to staff, faculty, and students there today. I've done this in other venues, and I think obviously the ability to do this remotely, virtually, provides a little bit of flexibility. I'm sorry I couldn't be there in person today, but hopefully you'll get a sense and a flavor for my background. So my career and my interest in engineering and meteorology has essentially been a dance for probably the last 30 plus years. The original interest is meteorology, but for reasons I won't get into today, I went the academic route, at least initially in engineering. I guess I just cutting to the chase. The idea of shift work and weekends and moving around the country working for the Weather Service didn't appeal to me at the time. This is going back quite some time. So with some reluctance, I did focus on the engineering, which as it turns out, I'd be remiss if I didn't say this at the outset that I couldn't have designed my career any better if I tried. It wasn't a random event. Obviously, decisions were made along the way. but I utilize pretty much all of my engineering skills, hardware skills, software skills, data analytics skills, as well as the domain expertise in meteorology almost on a daily basis. And so I think I chose the Jefferson project at Lake George because it's a really good example of a research project that, again, I've really had the pleasure to work on a multidisciplinary team across multiple institutions over the last 10 years. And I would say in my 30 plus years at IBM Research, this is probably the best research project that I've had the opportunity to work on. I've done some client work as well. I won't focus on that today, but I think this is an interesting project because it knits together various disciplines as well as makes good connections to to educational aspects that I think students would be interested in. Because I get asked a lot, from a private sector perspective, especially when I'm working with students and some faculty, to make better connections in what the private sector is looking for from a skills perspective and from just a marketability perspective for students. And so I think this will provide a good example of that. So, what is the Jefferson project? It's a multi-year partnership, which was initiated about a decade ago in June of 2013. And the focus is on understanding and managing, the complex factors around the ecology of the Lake George watershed, and in particular the lake itself. The focus, at least on the IBM side, is the monitor, model, and predict part of what we call the living laboratory. And it's really a project that encompasses, more than 60 engineers and scientists across multiple disciplines. It's a partnership among IBM Research, Rensselaer Polytechnic Institute, and the Lake George Association. So obviously IBM represents the private sector, Rensselaer represents academia, and the LGA is what we call an NGO, a non-governmental organization. They're the public-facing, aspect in regards to dealing with the public and in the public stakeholder interest in the various aspects of the lake. In this case, Lake George being the lake of focus. Now, I will mention, and I think I have a slide or two later on that will focus on, we've branched out to other lakes. So for anyone that might be familiar with Lake George, and I'll get into that in a moment, it's a very clean, pristine lake in upstate New York. And so people would ask, well, why would you start with a lake that's so clean and so easy? Why not start with something more challenged? And while that's a valid question, it really, the inception of the project started with, I think, the public and the stakeholder interest in the ecology of the lake. So Lake George has a significant historical aspect to it, as well as a tourism aspect. It has probably about a $2 billion a year tourism industry, which focuses basically on the south end of the lake, a very small portion of the lake watershed, and runs essentially from Memorial Day through about Labor Day, plus or minus a couple of weeks. But it's pretty significant from a New York State tourism aspect, but also from a lake watershed. The lake's a drinking water source. I think it's a class 1, or I can't remember the EPA class for drinking water source, but it's a very clean drinking water source. At the same time, it's a recreational source. There's power boating on the lake. There's sport fishing on the lake. Diving into the lake. Lots of activities in season. In the winter season, when the lake would freeze over, and that, by the way, occurs less frequently than it used to. The lake will freeze over completely. That's not been the case for about the past 10 years or so, where a couple of years I think it did freeze over, but there are many years where it does not. It's the lake is rather large. It's about 34 miles long and about a mile to 2 miles wide at its widest point. Runs north to south, actually flows south to north, which is a bit atypical of lakes in the area. It sits in the Southern Adirondack Park of New York State, which is a large maintained area, preserve, if you will. And so it's unique in that it's an oligotrophic lake formed by in the last glacial, period. And so there's a lot of unique aspects of the lake, and hopefully I'll be able to reference some of those as we move forward. So again, what is IBM's role in the Jefferson project? We have a history of innovation and invention. I have a slide or two that focuses a little bit on IBM Research in a moment, and a breadth and depth of focus and experience. as well as in developing enterprise and scalable solutions. So in the case of the Jefferson project, IBM's contributions include all the physical aspects of the environment, the science, technology, engineering, and math. That includes things that we call environmental IoT, Internet of Things. These days, it's the more common nomenclature is what we call edge computing. So having smart sensors out there, and I'll have a couple of slides that'll detail some of that. The environmental science and analytics. That includes, pulling the data back and doing analysis on that, as well as working with our Rensselaer colleagues on some of the academic aspects of the data. Physical modeling and simulation. So that's the meat of, certainly the area I spend a lot of time on: numerical weather prediction, hydrological modeling, and hydrodynamic modeling of the lake. That's a coupled model ecosystem. The hardware and software infrastructure. So I'm switching from my meteorological hat to my engineer hat there, because there's a significant sensor infrastructure and a computation infrastructure that supports the project. The systems engineering, as in my title, is part of where I spend my time. And visualization is a key component of how we deliver some of the content to stakeholders. So a little bit of background on IBM research, and I always enjoy presenting this slide because I get some surprises. I can't see you right now because I'm just looking at my screen. There might be a couple of surprised looks or raised eyebrows. IBM inventions in daily use, the ATM. Some of you may not be familiar with that. That was invented by IBM. So these days, with with Venmo and PayPal, perhaps we don't use ATMs quite as frequently as we have in the past, but certainly large segments of the population do. Computer DRAM, so the memory in your laptops, that was invented in IBM research, literally down the hall from my office. The fellow that invented it, he's retired, but he still comes to work occasionally as an emeritus. The excimer laser. I actually know Jim Wynn, who actually is one of the inventors of the LASIK surgery. That's obviously has a huge impact from a medical standpoint. And I guess most near and dear to my heart, I'm not going to go through the entire list, but the Fortran programming language was invented in the building that I work in. So Fortran, as many of you probably know, forms the computational core of pretty much all high-performance computing models, including numerical weather prediction. So the core of WRF is Fortran, while the rest of the infrastructure for WRF is wrapped in C and C++. For those that are interested in the software side, the actual numerical simulation and integration portion of WRF is Fortran. And that's also true for a host of other models like CFD models, computational fluid dynamics models, as well as electromagnetics, finite elements models, as well as many others. The hard disk drive in your computers these days are mostly solid state, but everything in the data center and everything in the cloud is backed up by rotating disk. I spent almost half my career in traditional engineering in a research project, research group called Magnetic Recording, where we did research in materials and systems around magnetic recording heads, magnetic recording media, and all of the associated aspects of that. In the interest of time, I won't go into the rest of this, but obviously you've probably read through the rest of this list as I was speaking. A number of notable, inventions going back many, many years. By the way, I'll just set at the outset, we can make this interactive, so certainly feel free to interrupt me with any questions if you like. Certainly, I'll do my best to leave time for some at the end. And again, since I'm not looking at a clock here, please keep me honest here and on time. As we start to run a little short, perhaps we want to leave at least 10 or 15 minutes for questions. Let me know where we stand time-wise, and I'll do my best. I tend to, I have a good number of slides here. I tend to speak fast, but I tend to speak too much, and Jana knows that quite well. So please keep me on task here, and let me know how I'm doing on time. So a little bit on our research focus areas. As you might expect, IBM's very focused on a couple of significant aspects: AI, semiconductor R&D, cloud computing, quantum computing. Environment and sustainability obviously is a core part of our what we call CSR or ESR, environmental and social responsibility aspects. And my group obviously is environmental science. I have colleagues that are computer scientists that are working on AI applications for climate and climate impacts. So really significant work done in the building. I'm at the research headquarters, which is about 30 miles north of New York City in Westchester County. The building is the headquarters for a research division of about 3,000 people, maybe a little bit more. I do have a map that I'll show of the locations for the research labs around the world. And here's that map. So you can see we're focused, all along the world, in Asia, Europe, Africa, as well as South America, our Brazil lab, and numerous locations in the US, including the Yorktown lab, where I'm based, the Cambridge lab, which is a partnership we have with MIT, as well as the Albany Nanotech, where we do significant R&D in semiconductor research and development, and the Almaden lab, which actually was the seat of our magnetic recording work going back a couple of decades. We sold our business in magnetic recording, I think, in 2005. But that really is where a lot of the magnetic recording work was done. And these days are atomic force microscopes, as well as other microscopy work, and a host of other materials work is done in Almaden. Zurich is one of our premier locations as well, as is a couple of locations in the UK and Ireland. And our newest labs are in Kenya and South Africa, 2 locations. And as well as you can see here in India, and our Tokyo Research Lab, which also goes back a couple of decades. So the environmental science research areas in IBM, this flow chart will give you a little bit of an idea of, in the context of the Jefferson project, making those connections. So since I'm a meteorologist, or at least half of me is, we always joke with my colleagues that everything starts with the weather. I get a little pushback from one of my colleagues who's a limnologist, actually. He says, well, it's all about water, isn't it? And we'll agree, but I'll say, yeah, but it usually starts with the weather. So in the case of the coupled model ecosystem that I referenced earlier, we have a numerical weather prediction model. We call our version Deep Thunder, but it is based upon WRF. Deep Thunder actually goes back and predates WRF. We ran on RAMS, for those that may be familiar with some of the history of numerical weather prediction models. That goes back a couple of decades. In the case of WRF, we've probably been working in WRF probably over a decade. We skipped MM5 and went directly from RAMS to WRF. Thought I might have heard a question there, so I'll pause.
No.
Okay. You can see here that coupling to the hydrological model. In this case, that's WRF Hydro these days. So the meteorological model, in this case, WRF feeds, precipitation predictions to the hydrological model, which then, which will then give us forecasts of runoff into the lake, and that's obviously important, as well as flooding in the area. And then we also feed both with the hydrologic model and the numerical weather prediction model, a hydrodynamics model, which actually does predictions of the circulation of the lake itself. Now, ultimately, this is about the ecology of the lake. So what runs off into the lake, the organics, the salt from, winter salting operations, organics from, certainly from the leaves and other, other organics flows into the lake. That has obviously an effect on the water chemistry, which affects the biology of the lake. So you can see also there that there's some aspects of connection to atmospheric chemistry, not so much in the context of the Jefferson project itself, but obviously more generally speaking for some of the work that, my group, my subgroup within environmental sciences, I'm in the atmospheric sciences group, focuses on. We've done some work in the past, with some clients on, air quality, as well as there's certainly some interest and has been some interest historically on wildfire. And obviously there are, weather drives is an important part of the drivers in that regime as well. And then you can see from a technology standpoint, some of the, this relates again back to making some connections to an academic environment for students, some of the aspects of the skill sets and the disciplines that get involved here. So from a technology perspective, that's high performance computing. One of the sub hats I wear under my engineer hat, I guess, packaging and observing systems, instrumentation. So I was involved with actually siting the instrumentation, some of the instrumentation around the lake, including about half a dozen weather stations that are instrumented that we built over the years around the lake, as well as you can see here some of the other aspects of the particular disciplines and the connections they make to both technology as well as academia. Ultimately, I'll just mention, you'll see there at the bottom next to ecology, algal blooms. That wasn't an issue when we started this work 10 years ago. Certainly not in Lake George. Lake George hadn't had an algal bloom. Over the last couple of years, it's had probably on the order of maybe one per year in the fall, typically. One or two of them have been what we call harmful algal blooms, which some of you may be familiar with, where you have a cyanobacteria in the algae, and if those things, if the bubbles, if you will, or the I guess the containers that hold those, if they burst at the surface of the lake, they can aerosolize, and obviously that can have real impacts on people swimming in the lake, people walking near the lake, even pets. So that's obviously certainly an issue to a much larger degree at other lakes. Some of the Finger Lakes in New York that we actually focus on, Skinny Atlas Lake and the Central Finger Lakes, as an example, we're running some of the model work there, and I'll get into that a little later on, as well as Chautauqua Lake in far western New York, which is near Buffalo. Obviously, other lakes that are really challenged, Lake Okeechobee in Florida, the red tides along the coasts, and we could spend a long time listing off many other water bodies, both in the U.S. and around the world, that have been increasingly challenged from an algal bloom perspective. So from a STEM and cross-disciplinary perspective, this, I think, again, speaks more to perhaps student interest. There may be some staff interest as well when you think about connecting to what we do in the private sector to, communicate that to your students. And Jan and I have had some conversations in that regard, trying to make better connections for students. From a science perspective, again, I won't go reading through all of these. You can read them faster than I can list them off here. Clearly on the atmospheric science side, biological side, in the case of the biology, RPI's expertise in freshwater biology goes back 40 or 50 years. They have a field station on the lake called the Darren Freshwater Institute. It's about midway up central on the lake. And we've pre-COVID, we had many opportunities to meet at that lake, probably once a quarter. We haven't so much since then, even though things have been lifted. I think people have got into a little bit of a new regime of working. It's easier to convene a meeting virtually. I miss going to the lake. I've been up there over the summer just on vacation for myself. Having been a native in New York, I'm familiar with Lake George. I remember going up as a kid. I brought my kids up there. It's a beautiful place to go. Even if you don't go on the lake itself, the area is mountainous in the Adirondacks and a really, really pretty area. But from a biology perspective, the RPI staff has had marine and freshwater biologists that have been doing manual sampling of the lake going back more than 30 years, and so they've got a long history and a large database. A limited sample size, obviously, in any given year, because you can only manually inspect so many areas of the lake. But one of the strengths of the Jefferson project is our ability to scale some of those measurements with an automated sensor web, and I'll get into that a little bit later. You can see here certainly there's aspects of technology, engineering, and mathematics that apply here as well. So again, and anywhere you see an asterisk there, we have team members that actually participate with a focus in those disciplines. So again, for those that may not be familiar, where is Lake George? I mentioned Southern Adirondacks, so the arrow that says you are here is the location of the Watson Lab where I sit. New York City, I think you can kind of figure out where that is. You can see the confluence there of Long Island and New Jersey. So it's about 3.5, 4 hours, north of New York City. Lake Champlain sits just north of Lake George, and in fact, Lake George, as I mentioned earlier, flows from south to north, flows into Lake Champlain. Lake Champlain, as an example, has about 3 dozen invasive species in it, both invasives from the standpoint of fauna, as well as obviously much more agricultural runoff. Lake George has about half a dozen, much less. So fortunately, there's a dam between Lake George and Lake Champlain. It's in Lachute, which is at the north end of the lake, and the Lake George flows out into the Lachute River, which flows north into Lake Champlain. If the water flow was the other way around, Lake George wouldn't be nearly as clean as it is. Obviously, the dam helps, but before the dam was built, the fact that things flowed from south to north and not the other way around really favored Lake George's preservation in a pristine state. So I mentioned earlier, Lake George is oligotrophic. It was formed, from the last glacial retreat. And Lake George actually is prior to that retreat was two lakes connected by a river. The river these days is known as the Narrows. It's part of the narrowest part of Lake George, where the current velocities are the highest, because it's it's certainly from a fluids perspective where you'd expect that to happen. And when the last glaciers in the area receded, they scoured out the basin completely and formed a single water body, which we know as Lake George. It's dimectic, which means it has a spring and fall turnover, where the lake actually has it has a stable surface and a stable bottom layer separated by a thermocline in the lake, which is where you have a rapid change in temperature. And each fall and each spring, you have what's known as a turnover, where the isotropic layers of the lake actually start to become turbulent and turn over. And again, that's not unique to Lake George. A lot of lakes are dimectic, but in this case, Lake George is a rather large lake. I mentioned the Narrows, historical significance. Again, some significant Revolutionary War battles were fought on the lake. There are actually Revolutionary War wrecks in the lake. Part of the work that we did at the start of the Jefferson project was to do a high-resolution topographic scan of the watershed, and that's I believe it's about 1 meter resolution. Even today, that's pushing state of the art. 10 years ago, it was almost unheard of to have a 1 meter topographic survey of the lake watershed. And the watershed is roughly what you see there in the diagram to the right, around the lake. That's a relatively large area where we had a plane, a plane flew over with a state of the art red laser with high resolution laser and did transects across the lake for many, many, days and weeks to actually actually measure the topography of the watershed. We also had a bathymetric study done of the lake. That was done. That's essentially on the order of tens of centimeters. And so there was a specially instrumented boat that was on the lake for multiple seasons. Obviously, had to come out of the lake in the winter when the lake froze over, but spent a lot of time on the lake. That bathymetric survey is so precise and actually scan the locations of the wrecks. Those data were scrubbed from the data set that were provided to any of the partners. In fact, even though we IBM actually paid for that survey, we on the team don't have access to that raw data, since the lake sits in the Adirondack State Park and obviously has influence not only from the state park authority, but as well as I believe there may be implications from New York State agencies as well. They didn't want people diving on the wreck, and so those data are held under lock and key. And any of the data sets that were provided to scientists or other stakeholders have those data removed, because there are literally, there are 18th century wrecks at the bottom of the lake that while some of the locals may be aware of those, they certainly don't want that information to become public. So again, enough of that, but I think you get the idea. It's a pretty unique lake from a number of standpoints, both geographically, hydrologically, historically, as well as from a tourism perspective. So what is the focus of the Jefferson project? I think I've given you a pretty good flavor for that, so I won't spend a lot of time here. Again, you can read this pretty quickly, but it's really about understanding, predicting, and enabling the ecosystem of Lake George. And that's really what we call, again, applying the technology, engineering, and science in a living laboratory. So as I mentioned, we started out in Lake George, but now we're operating on 2 other lakes in New York, and we have interest obviously from other both academic as well as other NGOs and organizations in regards to applying the technology. Now, while some of the technology, like on the software side, is relatively easy to implement and to scale, the sensor infrastructure, and I'll get into that in a few slides, certainly is not plug and play. I mean, some of it is custom, some of it is off the shelf, but it does require obviously manual installation, and we've built up a pretty significant infrastructure over the last 10 years. So some of the observing system challenges, I mentioned earlier, it's a distributed multi-sensor platform infrastructure with multiple vendors, multiple sensors. They're physically disparate deployment types in a really challenging terrain area. That picture gives you an idea. That's at the south end of the lake looking north. I believe that's probably on, I'm trying to think of the name of the mountain. It eludes me. Actually, my wife and I drove to the top of that in the summer because this picture I've been looking at for years and I hadn't been on the top of that mountain. It's a really beautiful area, but you can get a sense of the terrain around the lake and how challenging that can be both around the lake and then in the lake to deploy a sensor infrastructure. And obviously some of the requirements on the technology side, it had to be low latency. You know, this data had to really be collected and then sent back to the aggregation platform, you know, on a regular basis with, you know, a reasonable frequency. Some of the data, depending on the kinds of data we're talking about, could include, you know, relatively low frequency sensor data, soil moisture, soil temperature, or might include high frequency data like ADCPs, acoustic Doppler profilers. These are instrumentation units that sit at the bottom of the lake, anchored to the bottom of the lake. Think sonar in submarines. They actually in real time sense the currents, you know, vertically and horizontally in the lake, and those are used for studies of the water column. They're actually also used to a certain degree to help us verify the hydrodynamic model, to make sure the model is actually, you know, how well the model is performing. So in the context of weather, we think of weather stations or weather observations as verification sites for a weather model. So in the case of a hydrodynamic model, you know, the ADCPs, and they're very limited, there's only a couple of them in the lake, provide some points for verification. If you will, perhaps you might want to call it a sanity check, since there's not enough of these things. There's only 2 or 3 of them in a large lake. They're relatively expensive. They're not always easy to cite, and they do stream the data back to the collection platform. And I'll have a picture of that a little bit later. Let me pause here for a moment in case there are any questions. And I'm doing a time check, so it looks like we've got a little less than an hour. So I'm trying to keep myself on task here. So here's a graphic that shows some of the locations of the sensor platforms and some of the sensors and some of the statistics around the sensor sites. So we've got more than 50 sensor sites and over 500 sensors. It's probably well beyond 500. I would hazard a guess it's probably, you know, on the order of 800 to 900 sensors out on the lake, and those have been obviously installed over a longer period of time. That includes 4 vertical profilers, which are anchored pontoon boats, and I'll have a picture of one of those. 12 tributary stations where we have the major inflows into the lake. 11 weather stations. That includes both the land-based permanent stations as well as the weather stations on the vertical profilers. And then you'll note there, you know, quite a bit of data, over 50 gigabytes of data just from the ADCPs alone. 2 megabytes of data from the soil moisture and temperature data, and 900 megs. And again, that's probably over a gigabyte at this point of point observations, you know, over the history of the project. So it's a rather large database. This is not even getting into the model stuff. I don't have a statistic on that, but since my engineer job, I have to maintain our storage. We probably have on the order of well over half a petabyte of model data, because we don't throw away anything, or we try not to, at least. That's a real challenge. I've got a half a petabyte file system, and that may sound like a lot, but when you start filling it up, trying to find places to put those data, I've been uploading it to the cloud. That becomes obviously a great place to store data, but for scientists, there's a lot of latency to get those data back. So just as an example, one deep thunder forecast for the lake, which is typically a 72-hour forecast down to 2 kilometers, and a 36-hour forecast down to 333 meters, is probably on the order of 70 gigabytes of data. And so that's just one day. If you take a month's worth of data, that obviously adds up pretty quickly. And so those data then have to be stored somewhere. So if we're going to do a survey of the lake over a longer period of time, you know, accessing those data can be a challenge. So right now, as I think I mentioned, I'll get into in a moment, we have, you know, we do a lot of the computing locally on 2 high performance computing clusters that we have in the lab, our lab data center in Yorktown. But ultimately, where this is probably going to go is into the cloud, where now there's the ability to build a high performance computing cluster of at least the capability that we have. And once things are in the cloud, it becomes a little bit easier to manipulate and move data around, especially large volumes of data that we've aggregated over a long period of time. So here's a couple of pictures. On the left there, the vertical profiler at the top, and bottom pictures there. That yellow, the pontoon boat gets anchored in the lake in season. They have to come out. Obviously, they'll come out probably in about a week or two in November, and they'll go in the lake probably in early April, as soon as the ice melts on the lake. And even if the lake doesn't freeze over, we don't want to have a vertical profiler anchored in the lake, because it could get crushed, obviously, by ice flows. Those vertical profilers include a water column sampler, which works on an automated winch system, and that measures things like conductivity, pH, temperature, dissolved oxygen, chlorides, as well as total algal content. And so that little structure at the top, which we call the doghouse, actually houses the motor system for the winches, as well as some of the electronics for sending the data back. The mast on top is the Met station. That's a Vizsla WXT 530 single package weather station with an ultrasonic anemometer and wind vane, as well as a UV radiation sensor, and the full variable suite for meteorological variables. The center diagrams there you see are photos of the weather station. In the middle is our Cedar Lane station at the south end of the lake. Pretty unique. The bottom one there is actually on two rocky outcroppings in the lake. These are permanent weather stations in the middle of the lake. They're in the North Basin, one on Gull Rock and one on Whale Rock, which actually allow us to site a weather station. Now the challenge there becomes these are totally solar powered with battery backup. This time of year, as the days get shorter, it becomes more of a challenge to manage the energy budget, because those weather stations have to use a cellular modem to radio the data back to the aggregation platform at the lab at the Darren Freshwater Institute. So that becomes, a challenge, obviously, from an engineering standpoint and an energy budget standpoint when the days get shorter. As we move to the right there, you'll see those green objects. Those are ADCPs in the lab and one in the water there. Those are the acoustic Doppler current profilers that I mentioned earlier. We actually even had one mounted at the bottom of a boat, the Mini Haha, which is in season. There are rather large tour boats that tour the lake. And so we actually had a one season where we had actually an ADCP mounted there. Did I hear a question?
No.
Okay. And then on the far right is a picture of one of the tributary stations. This one sits at the Darren Freshwater Institute. That the stream that actually flows into the lake near DFWI, and that actually has a sampler in it with a conduit that runs into the stream that has actually the sensors, and then the water gets pumped back into the hut there, and where some water analysis is done, and then the data can then be radioed back via cellular modem to the aggregation platform. And you can see there it measures some of the same variables that the vertical profilers measure. I'm going to speed up a little bit here in the interest of time. This may be a little bit less of interest to everyone, but again, please stop me if something comes up that you'd like to know more about. The environmental, from an environmental IoT software overview, you can see on the right there some of the software aspects of this. On the left is some of the functional aspects. Diamond Point is what we call our sensor platform. So it's a single board computer, for those that are familiar with that, called a Raspberry Pi. For some of you may have heard of a Raspberry Pi. That's a full Linux platform on a small single board computer, and allows us to do Python programming, Linux scale work, to do what we call things like adaptive sampling. So I mentioned earlier, when the days get shorter, if you're managing a power budget, well, you're running that single board computer as well as those sensors off of a solar power battery backed up energy source. And so you might want to then adjust your sampling frequency during periods where there's not a lot of interesting weather or other interesting things going on, and if your power budget is going to be challenged, as it might be during the shorter days of the year. So here's just a photo of, on the left, of the diamond point. That's actually a very old photo in the old days where we actually had on the top of that enclosure, see that light green board? That was there's a Raspberry Pi sitting on top, and that was kind of put together by one of the engineers. In this case, as much as I would have liked to, I was focused more on the engineering of the systems level stuff. In my past work, I certainly done work at the level of boards and designing and building boards. One of my colleagues is also an engineer. He's actually finishing up his doctorate in interdisciplinary studies at RPI. So he'll be another hybrid like me, although focusing much more on the biological side, where I focus more on the environmental and the weather side of things. And then again, you can see some close-up photos there. On the far right is just an example of some earlier product work that we had in providing some of the outputs from some of the sensors on a mobile platform. That work, I think, has moved on as the technology has changed. But just gives you a sense of, from a sensor perspective, the ability to take some of that sensor data and then provide it to stakeholders. Let me back up one slide. Assembly Point on the right is what we call our aggregation platform. And by the way, both Assembly Point and Diamond Point are real places on the lake. They are both of which have historical significance. Assembly Point is where the colonists assembled their fleet when we had some of the battles with the British on Lake George during the time at the Revolutionary War. Diamond Point is on the west shore of the lake, probably about a third of the way up the lake. Probably some battles were done there. I don't know the history of that, but Assembly Point is really a good location. That's at the south end of the lake, and again has significant historical connections. So I mentioned Diamond Point being the sensor down end-to-end analytics. That's where we do, if I mentioned earlier, this idea of edge computing, what we call the environmental Internet of Things. Edge computing is where you have some power, computational power, that allows you to do things that go beyond just a data logger, where you're just logging temperature measurements or humidity measurements or water column measurements, and you can't change the frequency or you can't change the analysis. Well, with a Raspberry Pi, a Linux single board computer, you can actually not only change the frequency, but you can even do some on-the-fly computation there. And if you did some, for instance, let's just take if we want to read the ultrasonic rain gauge. Actually, in the case of the Weissler, I misspeak. It's an acoustic rain gauge sensor. You want to measure the rain rate. You can actually do some computation to do real-time rain rate measuring. And maybe that's significant, because if you got a convective event in the summer and your rain rates have ramped up, you may want to increase your sampling frequency so you can better capture that event from a temporal perspective. So just to give you a flavor from for the power of edge computing and what may be possible. The sensor network supports some of the key aspects of the research that we do, and there's a couple of examples here. So on the far left, you see the diagrams there, if you will, and I don't expect you to read the diagrams. They're a little bit challenging here, but we've actually sensed what's known as a SACE wave. That's an internal wave to the lake, and that wave flows. The waves flow some north to south, but actually some flow across the lake east to west. So when the sensor first picked that up, we thought that was quite interesting. Not perhaps surprising, especially to my limnologist colleague, since he focuses on water bodies. But when the hydrodynamic model actually simulated a SACE wave, we got really excited, because that meant that the model was onto something. It had sufficient spatial resolution, X, Y, and Z, to actually resolve that feature. The fact that you have these internal waves that bounce off the shorelines in the lake perhaps wasn't a surprise, but the ability of the model to resolve that certainly was. Now, what significance did that have? During the portion of the year where the lake is stratified, summer, for instance, we'll take that as an example, a SACE wave could disturb the water column. Now, why is that important? If you've got suspended organics in the water column, that could motivate an algal bloom, as an example. If you disturb the bottom with a SACE wave, where there's what we call detritus in the bathymetry. So you got a layer of mud at the bottom, and some of the organics have sunk to the bottom of the lake. You stir the lake bed up a little bit. Now you've got even more organics in the water column, which has a higher probability of motivating an algal bloom. Depending on the content of those organics, it might be a harmful algal bloom. You might motivate cyanobacteria or other bacterial forms into the water column. That becomes a problem. And I mentioned earlier, up until a few years ago, while there were, benign algal blooms in the lake, there weren't any harmful ones. There now have been, at least as I mentioned, once a year. I don't have any updates from this year. Probably my colleagues, two of which are based at the lake, they've probably not done an analysis yet on those data, but I would not be surprised if indeed there was yet another algal bloom this year. So that speaks directly to interaction with the public, interaction with the biology and the ecosystem of the lake. So again, these diagrams here sort of give you an idea. On the lower right there, you'll see an example of looking at shear currents with ice cover. So obviously, once the lake freezes over, now you've got no more no additional advective stress on the lake from winds. You've got no UV convective stress on the lake from UV short range radiation on the lake. That all shuts down. So now everything that's driven in the lake is driven by internal processes. Obviously, in years when the lake doesn't freeze completely over, you have some wind stress on the lake surface, which could mix down into the lake, although it's not a huge factor. But just gives you an idea of, in this case, again, looking at some of the currents in the lake. And again, I know it's hard to read these, but the right above on the right there, you can see to the left is ice covered and to the right is ice free. And you can see from the color outlines that certainly there are some differences in the currents in the lake when you have complete ice cover over a particular area. So, the idea of what we call the environmental infrastructure here, and again, I'm not going to spend a lot of time here, but I think the circular diagram on the right kind of gives you a sense of this idea of a continuous loop, everything from sensings and observation to model outputs to model ingest of some of the data and assimilation to archive of the data back through the telemetry, back to the aggregation platform, and then back to the stakeholders, and things like quality control, which is yet another perhaps function of what could be done at the edge in edge computing. If you're challenged because of data volumes or because your ability to transmit a large bulk of data via cellular modem could be challenged by things like signal to noise because you're in a highly challenging terrain, or it's the days are shorter, you've got a limited power budget, so you can't run the cellular modem for an hour. Perhaps that has implications for how much data you want to transmit. And maybe you obviously can only store a limited amount of data locally on the Raspberry Pi. You may have to be more selective in how you qualify those data, not only for actually having good data, but for the aforementioned example of just being able to manage your data volumes and from an aspects of transmitting those data back to the aggregation platform. Just doing a time check here. Again, I want to leave about 15 minutes or so at least. We've got about 40 minutes left. So this diagram, again, for the students, shows some of the connections for that diagram to aspects of technology. So hardware and software and engineering technology, and you'll notice there from the models, we're talking about programming languages like Fortran, C, and Python. From an IoT perspective, we're talking about, again, I mentioned the single board computer running Linux and the Python programming language, as well as technology including the single board computer, Python automation, the Linux OS. And again, just to give you a flavor for how this abstract diagram connects to real world technology and engineering aspects, and how that reach back then connects to things that students may be of interest. I know this particular audience is going to be focused more on the atmospheric side, but I presented this this kind of presentation to engineering students, to technology students, and so the power, if you will, or the beauty of the project, as I mentioned earlier, is it really has so much integration into different fields, and I think serves as a really good example of a multidisciplinary project, both at an abstract level, atmospheric science, engineering, technology, but what I'm trying to demonstrate here is that, at a boots on the ground level, okay, what programming language am I using? What kind of automation? What's the compute platform that I'm running on? Just to give you a sense of, of those aspects of the project. So another more conceptual diagram here, showing on the left the operational modeling platform that again includes the the weather, runoff and circulation model, and on the right, the observational platform. And the idea here that those particular aspects of the project do share data. Certainly the sensor data flows back and into some of the models, and some of the model data is used obviously from the standpoint of any work that we might do in the field and in verifying perhaps the ability of a particular event. So if we have a harmful algal bloom, we're going to be looking at the weather. And so just a little bit of a teaser that's, this is ongoing work by my colleagues and some work of mine to a lesser degree, looking at what are the weather regimes that happened before a harmful algal bloom. And what we found is generally a couple of days of calm conditions where there's significant solar irradiance on the lake. So obviously, September, October, to some degree, early November, the days are getting shorter. But if you've got a warm day and it's fairly calm, you didn't disturb the water column. If things are starting to have some buoyancy and come to the surface, now you've got perhaps a mixture of organics in the water column, as well as temperature and solar irradiance that might motivate an algal bloom, just as an example. So from an operational coupled modeling perspective, again, this gives you more of a pictorial of the models themselves and how they might interact. Deep Thunder, the weather model itself, providing things like wind, as I mentioned, radiation, precipitation, and temperature, feeds the WRF Hydro, the hydrological model, feeds the hydrodynamic model, which as well as the hydrology and runoff from the hydrological model, feeding the hydrodynamic model. The weather model does full 3D variational assimilation into the model. That includes obviously DA from the other models, and I'll get into that in a few moments, as well as some of the weather observations around the lake and surrounding area. I mentioned earlier the lake work that we're doing not only on Lake George, you can see in the lower left-hand corner, both including Chautauqua Lake in Western New York and Skinny Atlas Lake. Then again, in the interest of time, I won't read through all of this, but I mentioned earlier, we've been doing 333-meter forecasts, which is well beyond state of the art for several years in the Jefferson project. Now, arguably, that's in what's known in numerical weather prediction as no man's land, where sub 1 kilometer becomes a challenging area, not only from a predictive standpoint, but obviously at 333 meters, it's going to be really hard to verify that model. We did some limited work over a 2-week period, I believe last year, with the University of Albany. One of our collaborations is with the ASRC, the Atmospheric Sciences Research Center, and some of the staff at UAlbany, where we deployed a SODAR out on the lake. And the SODAR stayed out on the lake for about a week, on the shore actually of the lake, and did scans of the lake. And so we got an idea of some of the boundary layer in the lake water basin, where we didn't have anything above the surface there. And that work is ongoing. There's still probably quite a bit of data. We haven't spent enough time yet analyzing those data, but we, just as an example for the meteorologists in the group, the SODAR certainly did identify a low-level jet, over the lake during the period of time when it was there. That obviously would be certainly motivated by the mountainous terrain around the lake, where you've got subsidence depending on the time of day, coming down the lee side of the mountains into the lake. So that might motivate a low-level jet. We did see some evidence of that. What is the implication of that? Obviously, as I mentioned earlier, wind stress on the lake could potentially, if you had a long enough period of time, mix down into the water column. And if that becomes an issue, that could potentially motivate a change in the organics in the lake. Again, in the interest of time, I won't go through all of this, but again, I'm going to stop just for a moment in case there are any questions, and please interrupt me if you have any questions. All right, I'll continue. So I mentioned IBM's targeted weather model, Deep Thunder, and currently these days, based upon WRF, very high spatial and temporal resolution, customized to client needs. So we've been running Deep Thunder for a New York City domain for since 2001. I don't know any group anywhere in academia, private sector, or even in the government that's been running a ultra high resolution weather model at that resolution, 1 to 2 kilometer resolution for that long. And so while there's still a lot to be learned, I think our team probably has one of the longest histories of running this class of model over a particular area. Deep thunder these days in New York City is running at 667 meters over the 5 boroughs and part of Westchester County. Again, a lot of that I spend probably more time than I like on the engineering side, keeping the HPC model running and the platform running, and not as much time as I'd like analyzing the data. But just to give you an idea, I'll be presenting some of that work at the AMS, the upcoming annual meeting in Baltimore. Some from a systems aspect, and my colleagues will be presenting some of the case study work we've done. There was a extreme flooding event here in July of 2023. We did a case study on that, where actually we've run the model. I've developed a model for New York State, the entire state of New York at 1 kilometer. That's a really challenging compute problem. It's for those in the audience that might be familiar with NWP, the domain size is 750 by 750 at 1 kilometer. That's a real challenge. The data sets for one forecast are 0.5 terabyte. So I don't run them every day. And so some of the work we've done in looking at not only the Hudson Valley where the event occurred, but some other areas of the state that might have been impacted. 1 kilometer allows us to really start to see things at high resolution over a large area. And so my colleague will be presenting some of that work at AMS. We presented some of that work also for those that may be familiar with the New York State Mesonet Symposium. This was the second year. We participated both years. The New York State Mesonet is an integral part of some of the data that we utilize in our work. It's probably from a national perspective, it's patterned on the Oklahoma Mesonet, which many may be familiar with, but I think from a technology perspective, it's probably the leading edge Mesonet in the U.S. Both from a an instrumentation standpoint and from a deployment standpoint. So you can certainly see some of the work that's been presented, that will be presented at AMS, that focuses on some of the case studies. But in the context of the Jefferson project, this idea of taking the weather model and providing output for stakeholders. In this case, we utilize our own cooking, if you will, because we have fields that go out into the field to do sampling during the summer season and into the fall. So obviously, you don't want to be out on the lake in a boat if the winds are going to be blowing sustained at 20 knots. The lake is big enough that you do get a fetch, and you will have you'll have some white caps on the lake, and it's even in a 30-foot boat, it's not a fun way to spend your day on the lake. So and perhaps it may also have impacts on sampling the water column. And so utilizing the weather forecast, just from our own perspective, is an important aspect of what the weather model provides. I mentioned earlier, you saw obviously in the other diagrams the coupling to the other models as well. And the retrospective analysis, I think I gave a really good example of that in the context of the flooding event that we've done some case study work on, and that work continues. This snapshot just shows you an example of a deep thunder visualization. I apologize, I can't put it into animation because I don't have that coupled to this PowerPoint deck. But the arrows at the surface that you see there are model predictions of wind direction, and the color is the actual model prediction of wind speed. And you can see the legends there on the right. And then this snapshot doesn't show precipitation, but this particular forecast did have model predicted precipitation. And so the surface would be colored by precipitation. It would also show cloud water density. So you'd have a three-dimensional visualization. And this is the expertise of my colleague, who's the actual team lead, we've been working together for about 24 years now. And he's also an atmospheric scientist, but has unique visualization capabilities and expertise. And so we've been utilizing some aspects of that work for almost, the past 20 plus years. This snapshot just gives you a sense of that. It's not a typical way that you would see a weather forecast presented. You put this in animation and you'd watch the entire 72-hour forecast run forward in time in 10-minute time intervals. So that's high temporal as well as high spatial resolution. Here's just an example showing 10-meter winds to give you a sense for the Adirondack area in Lake George of the resolution challenges. So 3 kilometer resolution on the left, which is that's her resolution, 3 kilometers. That's significant for her. I mean, her runs for CONUS, but at the local scale in a complex terrain area, 3 kilometers is going to miss a lot. You can see 1 kilometer picks up quite a bit more, but even that pales in comparison to 333 meters, where you can see the wind flows across the ridge lines of the complex, mountainous area around the lake. You can see, lee side and windward side of mountains. You can see confluence and difluent flows at the surface that, aren't resolved. Obviously, as I mentioned earlier, verifying that is always going to be a challenge, even if the model were perfect, which it certainly is not. It will be a challenge to verify that. But this gives you a sense of, the ability of spatial resolution to help us understand, the physical system in and around the lake. The idea of weather forecasts at higher resolution, as I mentioned, also impacts the simulation of the lake hydrodynamics. So I mentioned, if you look on the right there, I mentioned, wind stress on the lake. That can certainly mix down into the lake. That obviously has the ability to disturb the water column. So just as an example of, of the impact of the weather forecasts and the weather itself on the lake water surface. These diagrams show you a couple of more visualizations of deep thunder. Upper left is showing wind speed across the lake. Now, the terrain is exaggerated somewhat, but it gives you a better perspective of the mountainous terrain around the lake as well as the lake watershed itself. Below that is a snapshot of, this was a forecast done in 2018 of showing the model predictions of wind gust. And you'll notice, the green colors are low wind speeds, where you'll see the blues, and there's a couple of dots of yellow there at higher speeds. Those are occurring where you think they might occur. They're occurring on the ridge lines and mountain peaks. So, qualitatively, it certainly verifies. Since we don't have weather stations everywhere, it's certainly a challenge to verify those quantitatively. And then on the right, a couple of more visualizations showing soil temperature, because the model includes the surface itself, as well as precipitation rate and solar radiance. And I lost control, I apologize, of my desktop for a moment here, and I'm not sure why. I'm just trying to regain control of that. Just bear with me one moment. Okay, let's.
Tony, I'm just going to jump in real quick with a little 10-minute warning reminder here. So we've got about 10 minutes, so we want to open it up for questions.
Great, Jenna, because I think we're getting close to the end there. So let me go to the next one, which will just show you a visualization that one of my colleagues presented. This is a fly-through of the lake watershed. This is done with a software package of visualization called Unity 3D. And actually, 2 of our team members have visualization expertise. And this was Mike Henderson's work, who's a mathematician. You're flying across the lake, but now the lake is drained. So this is looking at the bathymetry of the lake, and you're looking at the terrain around the lake. So you're flying from south to north across the lake. You can see the shallow areas of the lake. You can see the terrain around the lake. I always like including this visualization and animation because it's very cool. And to the left there for the students, you'll see in blue, scientific visualization utilizing Unity 3D. Or Unity 3D is an open source package, by the way. I can't speak to how easy it is to use since I've not used it myself. I don't think it's trivial, but it's very powerful. But this just gives you a sense, and some of the central locations are also noted in the lake. So in the interest of time, I'm going to move on. Here's a static representation using, again, Unity 3D of the weather model wind on the lake, the black arrows, and then the black arrows over the lake of the hydrodynamic model predictions of the surface currents of the lake. And yet another visualization, again, static image showing the stream flow into the lake, where you're seeing the major inflows into the lake and some of the impacts from a precipitation event, as well as the impacts on the stream inflow into the lake. And I apologize if I could animate this, you get a better sense of that. But I think you get the idea, and I want to try to make sure I leave enough time for questions. So once again, scientific visualization, including Unity 3D. Here's an interesting representation. You notice on the right, I'll have to back up and do that one again, showing a simulation utilizing the surface current predictions from the hydrodynamic model, showing an example of massless particles. So think ping pong balls on the surface of the lake. Let me show that again. And you'll notice they start at the south, and notice how they move during this forecast period and disperse across this. This is the south basin of the lake, but move along. So imagine you had an oil spill on the lake. And while that's never happened, there was actually a sewage overflow from one of the hotels on the lake. Actually, this animation, I think, was done right before that occurred. And so when this occurred, they asked us, could we do the same thing for that period of time? And it actually showed, how the overflow from the sewage system or the septic system flowed into the lake. Luckily, it wasn't large enough to create a problem, and it dispersed over time. But it was a good example of the potential. This was really more of a conceptual animation. It really is by no means a quantitatively rigorous, application of the technology, but it gives a sense of the ability to be able to, to do such things. Again, once again, scientific visualization. In this case, the software technology is called Leaflet. So some concluding thoughts here. The Jefferson project, as I mentioned, is really a platform, both from a living laboratory standpoint. I didn't mention earlier, and I certainly should have, the ability also from an academic standpoint. RPI brings students out during their summer field campaigns, where they have students come out. They work with the freshwater biologists. There have also been some limited level of undergraduate and some graduate students that have participated in the project over the years. But, really good example of a real research project, making real world impacts and its integration back into academia. It's certainly also a potential platform for skills and experience growth. And I think, again, just underscoring the bridge between academia and the private sector. So again, this is for perhaps the students in the organization, the private sector perspective on skills and opportunities. STEM skills, including especially programming, and analytics, and data science, are growing rapidly. And so if you're looking to backfill some skills to make you more marketable as a meteorologist or environmental scientist, I always recommend to students, those that I mentor and those that I present to, that those are always good skills to focus on. Mentors, as I mentioned earlier, I'm a big believer in mentors. I even late in my career, I have a couple of informal mentors that I work with, not only meteorologists, but those outside of the field that help me think outside the box. They've in fact been instrumental. One of the reasons I spend almost as much free time as I can working with academia was a recommendation made by a mentor I had, who actually retired from the company and was my manager years ago. And while I had interest in it, he said, "Why don't you spend more time on this? You seem to enjoy this," and it caused me to reflect on that. And the result was I really enjoy doing the kinds of things that I'm doing right now, presenting to groups of faculties and students, and helping to educate and work with faculty to do a better, to help better prepare students for work in the private sector. Continuous learning and skills is essential. I think you all know that. Professional organizations, again, I'm including not only the AMS, but from an engineering standpoint, the IEEE, which is the Institute for Electronics and Electrical Engineers, which I've been a member of since my early days as an undergraduate. AMS, IEEE, and the National Association for Environmental Professionals, you can see there at the bottom. And for those that may have interest, I can certainly provide some of the slides with these links. I have a curated list that I actually keep for precisely that reason. Private sector perspectives, this idea of new collar jobs. This really applies more perhaps to what I'll call 2YC, two-year colleges, community colleges, more than to 4YCs in big universities like the Ohio State. But I think there are still aspects of the idea of creating entry points for students at various points in their academic careers. So I'm a big proponent of 2YCs because I started my academic career at a community college. I didn't show that slide in the interest of time, but my first degree was an associate's degree in electrical technology before I got into engineering. And then the meteorological training academically came after that. The meteorology actually came before the engineering, but I won't get into that today. But I'm a big proponent of working with 2YCs. And in fact, one of the one of the AMS committees that I serve on, the Board of Higher Education, we spun up a 2YC working group that actually I chair. I work with academic colleagues at a couple of universities and community colleges in this aspect of the work. So providing entry points for students and along the entire spectrum of their academic career. Internships are very important as well. New learning paradigms, for those that may have heard of badges and e-learning, I'm sure some of you have on the student side, the idea of MOOCs, massive online courses, things like Coursera, YouTube, there's a wealth of information out there for tutorials and teaching yourself. All curricula, both at the 2YC level and even at the 4YC level, and meteorology and engineering are very similar in this aspect, are very challenged by trying to fit, some of the new skill requirements into a really packed curriculum. And in fact, Jan and I have had discussions about this, and she mentioned to me yesterday that you're working on a Python applications course, and that has implications because Python is the de facto programming language in the atmospheric sciences field. So how do we better prepare students? It's hard to take things out of a curriculum since it's jam-packed with all the math and science that atmospheric scientists need. And so a lot of that, or some of that, may fall upon the student to backfill some of the skills that they might find of interest and to prepare themselves for, employment, for instance, in the private sector. And I think that's my last slide. So I will stop there.
All right, thank you so much, Tony. We appreciate you. I'm gonna boogie out here because my kids have a commitment here in a little bit, but I'm gonna turn the time over to Madhu, who will help arrange the question and answer session from anybody in the room over to you. So thank you once again.
My pleasure.
All right, Dr. Praino, can you see the room? Maybe if you stop sharing.
Yeah, I'm going to stop sharing and I'm going to stop my my share here. Give me one moment and I'll be able to see everyone.
Maybe, thank you. We should stop.
Okay. Yes, now I can see the chat and I can see the room. So again, if there are any questions or comments or things you'd like to know more about, I'm happy to do that.
Okay, great.
Lights on up there.
Yeah. You want the lights?
Yeah.
Oops. Oh, this is too much, isn't it? Anyway, okay. Do people have questions? Yes.
Hi, yeah, thank you. I don't know if you heard the applause. Sometimes the thing doesn't pick up the clapping, so we just clapped. Just so you know. Okay.
Thank you. Appreciate that.
Yeah. I wanted to ask a little bit about, I'm sorry, this is not my field. I'm interested in how your project interfaces with the stakeholders that you mentioned. So for example, if you are finding that rock salt is causing a serious problem to water quality, can you work with, state actors to try to use more gravel or something? Like who does that kind of interfacing? Is it you, or do you have a special office to kind of do the outward facing stuff?
So I'm glad you asked that, because actually that's a good example of what one of the stakeholders, the Lake George Association, does in the context of the Jefferson project. They are the client stakeholder facing. And in fact, this idea of road salt came up early in the project, and a study was done with the New York State Department of Transportation. And it turns out, while you might intuitively think road salt would be a problem for the lake, while there is evidence of some runoff, it's not nearly as big a problem in Lake George. The salinity of the lake actually is lower than some drinking water sources for communities that draw water from reservoirs or from wells. So it's not really an issue for the lake. But that underscores, I think, a really good example. Another aspect of what the LGA, the Lake George Association, might do is work with local landowners, because there's a lot of older houses along the lakeshore with older septic systems. So that really has the potential for becoming a problem. There's actually two water treatment plants on the lake, one at the south end of the lake in the village of Lake George, which is where, again, most of the tourism is concentrated. And that lake, that sewage treatment plant, actually, it flows out into what's known as, I'm trying to remember the name of the marsh. It's eluding me right now. Dunham's Marsh. Obviously, that since it's a marsh system, you get additional buffering and cleaning of the water from the sewage treatment plant. I mean, it's not raw sewage, obviously, they do a really good job treating, but if you have a heavy rainstorm event, you can have what's known as a CSO, combined sewage overflow, where the storm drains in and around the village, will quickly exceed the capability of the treatment plant to treat the water, and the volume of water then goes through a bypass valve and flows directly out. Luckily, in the case of Lake George, Dunham's Marsh will further filter the water. The marsh area is a pretty large area, and before you get to actually the lake water body itself, there's probably on the order of I'm working from memory here, half a mile of marsh, and so then that's a rather large area. So that'll help. But all along the lake, up and down the lake, shores, you've got people with homes that are, older homes that could be 30, 40, 50 years old, septic systems that, could be a problem. People are using fertilizer on their lawns. That could be a problem. So those are the sorts of things that the LGA will work with the stakeholders and the public to help address and to help measure. And in fact, they will task us, RPI and IBM, to do a study. Say, can you guys take a look at, what are the issues around nitrates in the lake, or phosphates from the standpoint of sewage, or road salt as an example. So I thank you for asking that question, because I think it makes a really good connection back to one of the primary functions of one of our stakeholders and how important that is.
Thank you.
Is anybody else? Students, yeah. You need to drink more coffee before. Yeah.
You're gonna have to talk
You have to
really
talk
loud.
and maybe come here. From here. Okay.
Okay, go ahead.
Yeah, I can hear.
Yeah, you may have to repeat that question because I can't hear it.
Okay, and then you have mentioned that there's a environmental science research area at IBM, and also the atmospheric and ecological aspect of research area in the Jefferson project in Lake George. But in your research project, does it include the agricultural aspect of the Lake George and in the surrounding area? The lake or not? I'm just curious about it.
I only caught part of that from an environmental perspective, so I apologize. Madhu, maybe you can repeat that since you're closer, because I'm having I didn't catch all of it.
So she asked whether there is also an agricultural aspect that is that this project looks at around from the surrounding areas.
In the case of Lake George, and thank you for asking that question, because that's another good connection. Agriculture is not really a large aspect of the impact on the lake watershed area. I mentioned the septic systems from a residential perspective, but from an agricultural perspective, there's not a lot of agriculture around the lake. Now, one of the unique things that I didn't mention earlier about the lake, and you wouldn't know this from looking at a map or some pictures, but early in the project, we did a survey of the lake where we actually got in a boat and we spent the day motoring around the lake from the south end of the lake to the north end of the lake. And believe it or not, I was shocked in the North Basin how different the terrain is, because as you get to the North Basin of the lake, you're moving north, and you're actually moving north and east away from the Adirondacks. And so the terrain becomes a little flatter. And the composition of the soil changes. There's a bluish clay soil composition. So actually the water color of the lake changes. I won't say it's Caribbean color, but it had a unique turquoise tint to it that you don't see in the south end of the lake. And so the terrain being flatter, you might expect a little bit more agriculture. There's a little bit, but not much. So the lake is not impacted much by agriculture. On the contrary, however, if you go a little further north to Lake Champlain, huge agricultural runoff into the lake, phosphates and nitrates into the lake, and that obviously the terrain gets into the Champlain watershed, which becomes much flatter, and so now you've got more organics. Obviously, Lake Champlain is a lot larger than Lake George; it's a much larger water body, but the agricultural aspects and impacts on that water body are much more impactful than Lake George. So Lake George, fortunately, does not have that much impact from agriculture.
And then maybe we can. Yes.
So thank you. You have a really cool toy. Is there a way that you can let other people play with it?
I guess it depends on which toys you're referring to. I've got a lot of cool toys. My colleagues joke that I don't like to share my toys. If you mean the sensors and whatnot, those obviously, the stakeholders share those. Actually, RPI technically owns the sensor infrastructure. IBM owns all the compute. On the compute side, obviously for things like case studies, depending on the collaborative type work we might do, there might be the potential for some sharing there. But I guess it depends on which toys you're referring to.
Yeah, no, it's just there's an immense amount of it's just a phenomenal assemblage of stuff. I don't know how much. Could you tell us how much it costs on an annual basis to keep that going?
I actually don't know the answer to that question. Running the infrastructure. I mean, obviously, a lot of the sensors are low power devices, so they don't technically draw a lot of electricity. I would say the lion's share probably of the power budget is on the compute side in the lab that I manage in the data center because of the HPC clusters. Out in the field, those tend to be obviously lower power devices, so not so much of an issue. But if you aggregate that over 10 years, it's certainly not insignificant. I would say perhaps a significant portion of that includes things that RPI had already been doing for years. Going out and doing manual sampling. But obviously, if a sensor breaks down, if you got to remove it from the field and repair it and then replace it, that has implications for people's time, as well as perhaps replacing the hardware if it breaks and it can't be repaired. But I don't know on the order of, I'm sure it's on the order of millions of dollars over the life of the project, but that's not an aspect of the project that I'm familiar with.
Yeah. And I presume Deep Thunder is not open source, right?
It is not, but of course, as I mentioned earlier, WRF is open source, and Deep Thunder is based upon WRF. I mean, we have some unique aspects of the model configuration, including some of the DA that we do, and some of the way that we visualize and present the data. The data sources tend to be all public. We don't think we're using anything proprietary from a data source perspective, other than perhaps some of the limited amount of weather station data from our own network, but the New York State Mesonet certainly is available to academic partners. We, as a private sector partner, if we weren't collaborating with them, would not have access. But academia, they certainly have, they certainly do sharing. So those data are available. And then again, the other DA is done. I didn't mention because I didn't get into the real details of how we initialize and set boundary conditions for Deep Thunder. That we initialize on RAP. And we set boundary conditions on GFS. That's all NOAA data. So we couldn't do what we do without NOAA data. Terrain data comes from the NASA SRTM, shuttle radar telemetry, which was done, well over probably almost 20 years ago. But that's tens of meter resolution. So it's relatively high resolution topographic data. So some of the aspects of the way we configure and run our model are unique. I guess you'd call those the secret sauce and the trade secret. But the model itself and the way the model can be configured from various data sources is certainly not proprietary.
Okay, does anybody have any questions? Yes, there's.
I have a question. Are there any student internships? And what kinds of skills do you look for when you're hiring?
We actually we do. IBM Research has a limited internship program, and I unfortunately have to perhaps be a bit more cynical here in that ours is a smaller group, so we don't always have every summer the ability. On the computer science side, there's a lot of active a summer program that goes on, including traditional engineering and computer science. Our weather company colleagues did have some limited summer internships. For some of you that are familiar or keep up with things, you may be aware that IBM has sold a weather company. So they will be going back to a new owner, probably first half of next year. And so while I'm a little sad in that I won't have the ability to work as closely with them, we'll still collaborate with them. They certainly do, being a larger weather organization, certainly probably have a more active internship program. And as a mentor, I would, I can't stress, internships enough. And don't only think of internships in a traditional sense where you physically spend the summer at a location. This idea of virtual internships is becoming more popular. I think NOAA and the Weather Service may even do some of that on a limited basis. NCAR may do a little bit of that. So, I would certainly encourage you to investigate, those kinds of internships as well. IBM, again, we have a pretty active internship across multiple parts of the business, but they tend to focus more on areas that may be of less relevant to atmospheric scientists.
I have a question about how is it different doing research in private sector compared with in university?
That's a really good question. And years ago, when we started this project, I would say they were less alike than they are today. And I say that from the standpoint, as you know, if you're a grad student working with a professor, they might have to write a grant or get an NSF grant or any number of other grants to fund their research work. When I started in IBM research a long time ago, and probably it was even true 20 years ago when we started this project, there was a lot of core funding. And so you could do research in areas that you had core funding. You didn't have to worry about chasing money down. Well, that changed over the years, and over the last 20 years, I can tell you, we fought a lot of battles in the early parts of the Deep Thunder project that predated Jefferson by about 10 years. Deep Thunder, as I mentioned, is going on 24 years. Jefferson's about 10 years. We had to actually go search for clients and money, and we had to do quite a bit of that. So that's very similar to a professor, chasing down grant money and other sources of funding. So it's probably more like university over the last 10 or 15 years than it historically has been in IBM research. But I think that funding model has changed for a lot of even private sector organizations where they're looking for, separate sources of money, and there's limited what we call core funding. So sadly, it's more like university from a funding perspective than it had been. From a perspective of a university versus private sector, I, as a researcher, get to drive some of that. I have a little bit more flexibility. As you probably know, in an academic environment, the faculty drive a lot of that. Now, when you get to the doctoral level, perhaps, you can move the needle a little bit as a grad student, but undergrads and graduate students, by and large, follow the lead, obviously, in research areas that are of interest to faculty. I have a bit more flexibility in that regard, but it's probably less so these days because the IBM, as I showed earlier in that slide, is very focused on a couple of key areas. Cloud computing, artificial intelligence. I'll just choose two because those can actually do have relevance to the area that I work in. And since I wear these two hats as an engineer, and my graduate work in engineering was both focused on hardware and software, and I did that intentionally. So I spend a lot of my days doing Python programming. I don't probably work on the hardware as much as earlier in the project if one of the computers broke, we actually got in there with a screwdriver and fixed it, replaced the board or something. It doesn't happen as much these days, but I do spend a lot of time on the software side. So, since I'm a bit of a hybrid in that regard, I probably spend more of my time interfacing in those areas. But there's certainly applications for applying machine learning for things like bias correction in weather models, as an example. And things like cloud computing. I mentioned earlier, we've got two computing clusters. The Jefferson project runs on a compute cluster, which is probably about 4 or 5 generations old of hardware. It's not new hardware. It's a couple of hundred cores. It's maybe 200 or 300 CPUs. Now, that might sound like a lot to you all, but in the context of running a numerical weather prediction model, that's not a big cluster. If I want to run New York State at 1 kilometer that I referenced earlier, I can run it on my other cluster, which is newer technology, and it's about 384 cores. But it'll take, if I want to run a 72-hour forecast on that machine at 1 kilometer for all of New York State, it's going to take me about 18 hours. That's really not practical from an operational standpoint. The rule of thumb is you want to get 1 day of forecast done in 1 hour of wall clock time. So that's not really very practical. But if I port that model to the cloud, I now have the potential for applying a much bigger machine to solve that problem. And so now maybe I can run a 1 kilometer New York State forecast for 3 days in a couple of hours. My background, obviously in technology and engineering, allows me to work in those spaces. But you know, an increasing part of the atmospheric science community is starting to focus on AI. You know, NOAA has, you know, they have workshops on AI. And again, you know, you can reach out to Professor Hauser. She knows how to find me. If you as students have interest in some of the links back to some of the things that I referenced, I could certainly share those with you. So, you know, from an atmospheric science perspective and environmental science more generally, those are, you know, those are areas that certainly connect from a technology and a tools perspective to things that atmospheric scientists would utilize to, you know, in their work.
Thank you. Okay, thank you so much, Dr. Praino. It's time. And thank you for your talk and for the question and answer. So we'll clap again. Hopefully you can hear us.
I can.
Thank you so much.
It was my pleasure. And again, any follow-ups, you know, let Professor Hauser know. Be happy to do that. But thank you for inviting me and for your attention today.
Absolutely. Thank you so much.
Sure.
Thank you. Bye.
Bye.
Shall we stop recording?
Something happened.